This video was prepared by Hani Tanyun Sin, Hao Xiang Ying, Hilary Lee Yi Han, and Tua Ken Yi from Kolej Matrikulasi Melaka under the supervision of Madam Saria Ali. The ocean covers over 70% of Earth's surface and is essential for life, regulating climate, supporting biodiversity, and providing food and livelihoods for billions. It absorbs carbon dioxide, produces oxygen, and maintains the planet's environmental balance. Despite its importance, most ocean activities remain unobserved. Over 80% of the ocean is unexplored, making human monitoring alone impossible. This creates a major gap, allowing illegal fishing, pollution, and ecosystem changes to go undetected, which can harm marine life and weaken the ocean's role in regulating climate. Closing this monitoring gap is critical to protecting ocean sustainability and ensuring a stable future for our planet. To address the ocean monitoring gap, advanced technologies are being developed to enable continuous, large-scale, and real-time monitoring of ocean environments, supporting more sustainable ocean management. The first goal is to expand observation capacity, allowing vast ocean areas to be monitored continuously beyond human limitations. The second goal is to detect environmental threats early by identifying pollution, illegal activities, and ecosystem changes quickly and in real time. The third goal is to provide reliable data to governments, scientists, and conservation organizations to support informed and sustainable decision-making. To achieve these goals, technologies such as satellite remote sensing, artificial intelligence, and ocean robotics are increasingly used to monitor the ocean more effectively. One example of a satellite used to monitor ocean activities is Sentinel-1. Sentinel-1 uses synthetic aperture radar, or SAR, a type of active sensing technology. In this process, the satellite sends radar signals toward the ocean surface. When these signals hit objects such as ships, the signals are reflected back to the satellite, allowing the system to detect and locate vessels even at night or during storms. The satellite then transmits the collected data to ground stations on Earth, where large data sets of ocean image and vessel locations are stored. Artificial intelligence is then used to analyze this satellite image. Machine learning algorithms compare vessel movements with non-fishing patterns to identify suspicious activities. If a vessel is detected fishing inside a protected marine area or operating without identification signals, the system flags it as a potential illegal fishing activity. Authorities and environmental organizations can then use this information to investigate and enforce marine protection regulations. Satellite monitoring therefore enables faster detection and response to illegal activities in remote ocean regions. A study published in the journal Nature found that approximately 72 to 76% of industrial fishing activity was not visible in public tracking systems. By combining satellite imagery from Sentinel-1 with artificial intelligence, researchers were able to detect vessels that had previously gone untracked, revealing hidden fishing activity and improving the ability to monitor and protect marine resources. This demonstrates that the system is already being used effectively on a global scale. Another important solution for ocean monitoring is ocean robotics. Unlike satellites, which observe the ocean from space, underwater robots can operate directly in the water and collect detailed information from environments that are difficult or dangerous for humans to access. One example is Sentry, developed and operated by the Woods Hole Oceanographic Institution. Sentry is designed to explore deep-sea environments at depth of up to 6,000 meters, enabling scientists to study regions of the ocean far beyond the reach of human divers. Before deployment, scientists program a detailed survey route into Sentry. Once released, the AUV follows this path autonomously, using onboard navigation systems, including inertial sensors, Doppler velocity logs, and acoustic positioning, to maintain precise positioning at a stable altitude above the sea floor. As it moves along the survey track, Sentry collects data with multiple instruments. High-resolution cameras capture detailed image of the seafloor. Sonar systems map terrain by sending sound pulses and measuring the returning echoes, and environmental sensors record temperature, salinity, and chemical properties of the water. Typical missions last around 20 hours, during which the vehicle surveys large areas of the seafloor and gathers thousands of image and environmental measurements. This data has been used in scientific research to map seafloor geology, investigate hydrothermal vent systems, and study deep-sea ecosystem, providing insights that would be impossible to obtain through traditional human exploration. Advanced ocean monitoring combines satellites and underwater robots to provide comprehensive coverage of the ocean. Sentinel-1 satellites track surface vessels and monitor large areas continuously, even through storms and clouds. Sentry, an underwater robot, explores beneath the surface, capturing high-resolution image, sonar maps, and environmental data that satellites cannot reach. Together, they expand observation capacity, detect threats in real time, and provide reliable data for sustainable ocean management. Despite their effectiveness, some challenges remain because satellites can only revisit the same area periodically, and underwater robots are limited by battery life and mission duration, which restrict how long they can operate before returning to base. Future improvements, including more frequent satellite coverage, longer-lasting AUVs, and better AI integration, will create a real-time, connected monitoring system. By monitoring the ocean beyond human limits, we can protect ecosystem, manage resource sustainably, and ensure a healthy blue future.